some of the questions that we already have in the Slack. So to Emma, there is a question by Markus Witkowski. Red supergiants in general show different silicate dust features in the mid-infrared, from narrower to broader features. For example, work by Speck et al. 2000. So do you see such different features in your sample, or is the feature more uniform for this sample of the same metallicity and initial mass?
Yeah, so as I replied in the Slack, we actually don't have the spectral resolution to differentiate between the shape of the silicate features. We can just say that it's there rather than what it actually looks like compared to other ones.
Thank you. So I see that you answered a couple of questions, but I will read them just in case. I mean, I don't know whether to read them. So just in case someone wants to add something. So there is this other question by Tomek Kaminsky. Real supergiants do not have spherical envelopes. So does this influence dust masses from radiative transfer modeling? Do you have any idea of how masses do from dusty would compare from realistic 3D models?
Yeah, so we did actually look at this in a paper a few years ago. So we made some models using the moccasin code, which is a 3D code, and we put the clumping factor up to like a ridiculously high level, and compared what mass loss rates we'd get compared to using the spherical shell. And we actually found there was like very little change between the mass loss rate that you find from this, because the thing that doesn't change is the total dust shell mass. So unless the dust shell is like super optically thick, which in general it isn't for these objects, you can recover the same mass loss rate depending on with a spherical or a clumpy shell.
Thanks. If someone wants to speak, please raise your hands. I don't know whether I can see you, but someone will for sure. And okay, the next question is from Rob Ishak, which was about the use of mass loss rates in stellar evolution codes. In which regime would you expect your mass loss rates to be useful, and whether you can use them at lower luminosities, I would say, on the AGB and red giant branch?
Yeah, so I wouldn't use it for AGB and RGB stars. So the stars in our sample are between about 10 to 25 solar masses. That's what we calibrated the prescription from. So yeah.
Okay. And how do you mass loss rates compare with those from Groenewegen in 2009, which I think he also analyzed both like red supergiants and M stars in AGB stars?
I think similar numbers. Yeah, I can't remember the numbers off the top of my head, but they weren't massively divergent.
Okay, thanks. And the next question comes from I cannot pronounce this surname, I think, properly at least. So sorry for butchering it, but it's from Salt Crest, which was about do you consider rotation in your models, in your work? And he points to a work in which they argue that this combined problem is sensitive to main sequence mass loss rates. So do you have something to say about that?
So
or maybe you want maybe if you want to I mean, sorry, if Salt wants to make the question himself, that might help to make it clearer than I made it myself. I don't know whether he's raising his hand because I cannot see. Okay, so please go on.
Salt raised his hand. You can speak now.
Yes, thank you. Can you hear me?
Yes.
Yes, perfect. Yeah, so basically my question is whether or not you consider rotation in your models. And the reason why I asked this is because on the main sequence, the mass loss rates pretty much determine some part of the subsequent evolution. So if some of the main sequence mass loss rates are a bit different, then you not only change the mass of the star, but the angular momentum content of the star. So how much rotation is stored in the star can, of course, affect subsequent evolution.
Yeah, so are you saying that because of the rotation, it mixes the star up and makes more blue stars? Is that what you're saying?
Well, yeah, I'm saying it's sensitive to that problem. So it's difficult to draw conclusions if we consider all the uncertainties because essentially the way I see it is that the seeds of the uncertainties are planted on the main sequence, and then we need to explore all this big parameter space to be able to draw conclusions.
I think looking at rotating and non-rotating stellar evolution models, we'd find that the total mass loss from the wind would still not be enough to force the star back to the blue. Yeah, so not explicitly is the answer, but I still think that the mass loss would have to be like a factor of 10 higher.
Okay, thanks. And the next question comes from Graham Harper, who is asking whether has someone tried to model Betelgeuse multi-wavelength dust images. Is there someone who wants to comment on that? I guess that sounds like a no, huh? Okay. Okay, the next is just a comment about Jaco, who is complaining about the details, but then and then comes Curtis William, who mentions that the observational evidence for the kinks in the initial final mass relationship derived by Marigo and collaborators is based on a single data point. So, and he mentioned that they are working on a large sample, I think, which is interesting. Also, I want to point out that I'm not so sure that the initial final mass relationship is just a function. I am not so sure that it's only one value for a given initial mass. It looks much more than there is an intrinsic scatter. But do you want to comment on that, Curtis or David?
So maybe I comment. Yeah, I think you're absolutely right. I think the initial final mass relation is it's a mess, right?
Yeah,
but
it looks like that,
I think that there's some flexibility in there, that there's something that we could be missing that might help us to understand the PNLF.
Okay, I see that you answered to that comment. So do you want to comment something on that?
So the comment from Curtis is that basically it's the kink in Marigo's initial final mass relation is based on 1 point, 1 cluster. So it's there's work ongoing there, but it seems as though the follow-up, which I think Curtis is a part of, seems to verify that cluster's results. So there's potential there that this is a real effect and some missing physics that we don't understand. Maybe Curtis can comment more on that. I'm not an expert on the initial final mass relation by any stretch.
Can y'all hear me? Yeah, there I go up on the screen. Yeah, so basically, I talked with Paula and Marigo, and their conclusions are based on not just one cluster, but one single white dwarf that's like 2 solar mass progenitor, but has a lower mass than, or has a lower white dwarf mass than the 1.5 solar mass progenitors. Yeah, this is just really hard work. And one of the problems that I'm dealing with and why it's so slow is that getting white dwarf masses is fairly straightforward, but separating the field white dwarf mass distribution from a cluster white dwarf population is extraordinarily difficult. And Gaia is of limited help because most of these white dwarfs we're dealing with are 20th magnitude or fainter, which is below Gaia's limit. So I'm working on this problem. I'm not nearly as fast as I would like to. And Calorai and I guess their team are working on it as well. I don't know when additional data will come out.
Okay, thanks. Okay, the next question was about the proportion of binaries in young stellar objects and main sequence stars, I guess, of low mass main sequence stars related to the planetary nebulae ones. So do you want to comment on that, David? Sorry.
Sure. So the exact binary fraction along the main sequence is challenging to derive, but the best compilations from the literature seem to show that there's a sort of steady decline from high mass O and B type stars, which are almost entirely in binaries or higher order multiples, down to the lower mass end where solar mass stars are roughly 50%. So this is probably, I skipped over it too quickly, but this was what I was trying to get at in my talk, that if only 50% of planetary nebula progenitors are in binary systems and only a subfraction of those are expected to interact, probably only 20% of those, so 10% of the total of solar mass stars, then that's difficult to make fit with the hard observational lower limit of 20% that we see inside planetary nebulae. So there's at least a factor of 2 discrepancy there. And if you actually do the statistics
sorry, can you a factor of 2 discrepancy between
between the maximum number of, based on the distribution of the number of binaries and the period distribution of solar mass stars, you would expect a maximum of 10% to undergo a common envelope.
Okay.
And yet we see at least 20% inside planetary nebulae.
Okay, perfect. Now I see. Okay. Okay, so, and the next question is going back to Emma's talk, is about how does, and this is very interesting because I think this is the same for red giants. How does one relate these instantaneous mass loss rates from the time average ones that during the red supergiant lifetime? In other words, okay, so how do you relate the episodic mass loss rates to those, to the average ones, I think?
Yeah, so the mid-infrared excess mass loss rates are basically, they are time averaged for over the order of like a few decades, maybe like 100 years. So they aren't completely instantaneous. And also, as I said in the talk, when we use red supergiants in a cluster, it's kind of like seeing the same star at very slightly different phases of its evolution. So you can track how the mass loss rate changes with evolution. So any episodic mass loss rate, because we don't see it in the clusters, must just be ridiculously short. So it probably wouldn't make any difference at all, really.
Okay, so the next question is by Tim Lawler. I don't completely, do you want to present it yourself, Tim? Because I'm not so sure I will state it properly. Yes.
Hi again. Yeah, I was just wondering about the evolution models, and so like what state the core gets to in the end, because some ended at the red supergiant side and some move back to the blue, and so are they getting to the same? So evolution models, like I guess they can only go so far, right? Because there's this hydrostatic equilibrium requirement. So where do the cores end up? Do they all end up in the same, the same place, I guess?
So we evolve these models to core carbon burning, but we actually haven't looked at the structure of the core or anything. So I don't have an answer for that yet.
Gotcha.
Yeah.
Okay.
Okay, so the next comment is by Jaco. I think this is related with the previous one, which is the episodic mass loss rates and the short duration phases are easily missed. Do you want to comment on that, Jaco?
Well, it could be episodic, but also just the final stages of super winds. And Emma commented on that you may just make a different type of supernova. But those supernova constraints can be very, very useful for that. But you do have to do a proper statistical study, like she's done with Ben Davies, for instance, for that particular problem. And that's quite important whenever we look at small samples, which are either because, for instance, you've got a small number of sources within parameter range, or because of observational limitations, you have to account for small number statistics, and you tend to then just miss those extreme phases.
Okay, thanks. And the next comment is by Curtis again, and this is, to me, this is particularly interesting because I work in hydrogen efficient stars for a long time, and he mentioned that they have a referring paper. They have a paper in referring on the initial final mass relationship of hydrogen deficient stars, and that their preliminary results suggest that hydrogen deficient white dwarfs are 0.07 solar masses less massive than hydrogen rich white dwarfs, which is like more than 10%, and he's skeptical of the results about whether they will stand additional data, but he's asking for physical ideas about that. And this is again, this is a very interesting topic, because usually white dwarf masses, hydrogen deficient white dwarf masses, have been shifting from more massive to less massive than hydrogen-rich ones, at least as far as I have been involved in the field. So if you want to comment more on this, Curtis?
Yeah, so I mean, it's pretty much stated. I don't want to dominate the conversation here, but our results are mostly driven by a single white dwarf, and that's Procyon B. But Procyon B is so amazingly well constrained in terms of its mass and ages that I just don't, I can't throw it out of the sample lightly. So, I mean, maybe we should wait for the refereeing process, and I can, and I'll definitely post this on the AGB newsletter. But all the indications I've seen say that post AGB stars should not lose an extra 10% of their mass, maybe 1%, but not 10%. So I'm just throwing this out as looking for ideas.
For sure. I mean, post AGB stars cannot lose that much mass, at least not through winds, for sure. Okay, so this is only based on one white dwarf, or is it also like a cluster, some, but not clusters, because, or does it involve any other? Because you stated like as a general property, that's why I'm asking.
There are 5 white dwarfs total in the sample, most of them from M67. Again, these data aren't published yet, but they're in refereeing, and most of them are falling below the DA, the hydrogen-rich initial final mass relation, by a little bit, but the error bars are large enough that you could claim it's uncertainty. Okay. So it's really Procyon B that's driving it, but there's no way to bring Procyon B into line with the known initial final mass relation.
In which initial mass range would this be?
This is across the entire range that I have, which is from about 1 to 4 solar masses.
Okay, so because the very tricky ones is between like 2 and 4. This is really unconstrained. This is the initial final mass relationship is just the mess there.
Right.
Yeah. Okay. So thanks. Someone wants to comment on this? Okay. So there is a philosophical question by Jared Coulter, which is, so what should we modelers do in the stages where mass loss rates are ill-constrained? Do we vary mass loss and explore model dependencies? Are there better ways of being agnostic? As far as I understand, I have my personal opinion. I think we have to vary. I mean, if they are ill-constrained, then we should allow our models. And most of all, I think that the key point here is to tell our colleagues that our models are not really predicting some things, but really waiting for observations to constrain them, because this is sometimes something which is unfortunately misunderstood. There is some people think that stellar evolution models predict much more than they do. I mean, they do predict things, but there are significant uncertainties, and they have to always be taken into account when presenting theoretical results, I think. So does someone want to comment on this? Is this some of the people doing stellar evolution models wants to comment on what to do in this case with the mass loss?
Tim had still his hands up, so I've allowed him to talk. I don't know if that was a legacy hand.
Legacy hand. Tim?
I'm sorry. I think my hand must still be up from earlier.
Okay.
Sorry about that.
Okay, I think that was the last question. Does someone want to raise some issue here? We still have some more minutes to discuss, or maybe. Jaco, yep, please.
Well, not really to make a point myself, but I would really like to see the discussion continue on how the end products constrain the previous evolution, both of the star itself and the mass loss. And for instance, talking about the planetary nebulae and those central stars. So there's a lot of attention to the binary interaction, but what are the implications for single star evolution is I think an equally important question, because not all stars have a companion, and in particular the sun doesn't. So if you want to know what the sun will do later on, which I think we all do, then we have to both look at what binary interaction does, as well as still what single stars do as well. Of course, the binary interaction is also important at a massive end. We haven't heard so much about that here. Maybe somebody wants to comment.
I would say, like, there is something I like to mention about that, is that even though we know that binaries play a role, there is also the thing that it's clear that single stars should also create, I think, planetary nebulae, because otherwise we really need to explain why they do not, because the models do in a way predict that they will create planetary nebulae. So I think that this is an interesting point to mention. That is, it looks to me, and I would like to know David's opinion on this, but is that we have really a mixture. So there's really some planetary nebulae which are binaries, and some others which really arise from single star evolution. And in particular, I would like to know David's opinion about this thing. Usually people really relate non-sphericity of the planetary nebulae with binarity, and I don't know to which extent this is really something that is so clear, or how do you think this is the situation? Can you really say that anything that, I mean, any planetary nebula that is not spherical comes from a binary, or is shaped? I mean, and the difference between being shaped by the binary and being created by the binary.
Yeah, so this is an interesting problem, right? So I think it's fair to, I don't think anybody, maybe only some very extreme people, would claim that single stars cannot produce planetary nebulae. But I think we have an issue that if you look at the observed population, and also the fraction of binaries among that observed population, it doesn't fit with the expectation that all of the stars that our models predict will make an observable planetary nebula, will make a planetary nebula. What the exact discrepancy there is an open question. So I referenced in my talk a paper by Max Mo and Ursula De Marco, where they do some rough population synthesis, sort of back of an envelope calculation, and they find that essentially, based on the observed population and the binary fraction, only 1 out of 6 of the stars that we think should make a planetary nebula, an observable planetary nebula, actually will make one. And that's a pretty large discrepancy. So, and there are some other statistical ways of looking at it that make the situation even worse.
And I think
so the question becomes,
David, can I ask you something? I mean, I guess this is even worse if you include like updated tracks like mine. This problem might be even worse, I guess.
I'm not sure it will change too much.
Okay.
In effect, but it'd be interesting to check. I mean, there's some extreme assumptions there particularly in terms of the visibility of a planetary, right? Because we're talking about observable planetary nebulae, not naked white dwarfs, which clearly do fit with the models. We see enough white dwarfs that they fit with the main sequence population. So the question is, if that is the case, and we do have a factor of at least a few missing of planetary nebulae, maybe 6 if you take the Mo and De Marco paper, then which are the stars which fail to produce planetary nebulae? Considering we see an overabundance of close binaries, that would seem to indicate that the population, or from which population the stars fail to make a planetary, must be the single stars. So which single stars? Is it a question of mass? Is it simply that we don't understand the prior mass loss, for example, and such that by the time even with your faster evolving post-AGV tracks, is there not enough material there, or not enough previous ATP mass loss surrounding them for us to see a visible PN?
Yeah, okay,
or is there something?
It's a great way of putting it. I mean, which ones are failing, and I like this way of looking at the problem. I think, yes.
Yeah, so I think this is a big question for us to answer, and I don't see a clear solution other than the fact that it seems like binaries aren't failing; they're overly successful.
So, Jaco, you want to mention something? I think we are already running out of time, or
Well, just because I thought, Marcelo, you asked specifically about the non-spherical PN, whether all non-spherical PN are a result of binary interaction, or whether there are also non-spherical PN that come from pure single star evolution.
Yeah. Okay. So I forgot that second part of the question, but so I think there's an important thing for us to distinguish here, and that is when we talk about binarity, what do we actually mean? What is the minimum mass of a companion that we need for us to say that it's a binary? Because even Jupiter mass planets relatively close in, swallowed by a PN progenitor, will have some impact on the mass loss, be that enhanced mass loss or shaping the mass loss, perhaps only slightly. But so if we include this in our classification of binarity, in which we say that 80% of stars are aspherical, well, at least 80% of stars have one or more planetary or stellar companions. So can we make that match? It's interesting to say that the bipolar planetary nebulae fraction is about 20%, give or take, and the fraction of close binaries is about 20%. So that means that we only have this deficit of 60% where there's some deviation of sphericity to explain. And we don't need to invoke solar mass companions for all of those. Perhaps in some cases, that could be driven by a substellar companion.
I brought in Arturo, who had his hand up. Is he allowed to speak before we finish?
Please, Arturo, can you speak?
You should be able to speak.
Hello?
Yes, now we can hear you.
Can you hear me? Well, just a comment on the statistics, David. For a proper statistics, you have to take a volume. And from Gaia, we know that the sample of planetary nebula are only complete up to 2 kiloparsecs. So there are a lot of observational bias. So when you take all planetary nebula and make statistics, you are mixing up completely different samples. So at least you do at a limited distance, the statistics doesn't have much sense.
So which statistic are you questioning, Arturo? The 20% binary fraction?
Everything you do with a whole sample of planetary nebula, because maybe you have more brighter planetary nebula. For instance, this large planetary nebula, very bold, that have very hot, hotter than 100,000 K central stars, you only see up to 1 kiloparsec. So if you have planetary nebula up to 1 kiloparsec and up to 8 kiloparsec, probably you are not going to see this kind of objects.
Okay, so I still miss the which statistic you're questioning. Are you questioning the 20%? binary fraction.
No. I mean, this is a comment in general.
Because the 20% binary fraction is supported by Gaia. If you look at Shawnee et al. from this year, even though Gaia can only give us some statistics on variability, it seems to support exactly the same binary fraction that we find with Kepler, exactly the same binary fraction that we find with Ogle.
I'm talking in general, that when you do statistics,
and in any case, Arturo, sorry, I don't mean to interrupt you, but in any case, this is a hard lower limit, unless you are claiming that in any of these populations, in the Gaia population, in the Ogle population, in the Kepler fields, that we are completely insensitive to a particular type of PN, then that hard lower limit of 20% is still there.
Yeah, okay.
So yeah, unless it is that we are not complete to very large, very faint PN in one of these samples, which I mean, as you say, the Gaia is good for several kiloparsec. So, but in any case, we are also from the ground trying to use the 2 kiloparsec sample, which was initially derived by David Frew and is now supported by Gaia, to make further statistics on the binary fraction, but it's basically the same.
Okay, I think we have reached the time. Am I right?
Yeah. Yep. So we are toward the end of this day 3. Thank you so much, Marcelo, for having greatly chaired this session, and thank you, Emma and David, for your great talks. I again encourage you to continue the discussion. It's going great on Slack. And just a quick announcement. Tomek had this idea to build a new channel on Slack called Contributed Talks Promo. Please go there. I have to invite you one by one, manually inserting your email. It's just on the channels among Slack. So just go in there and promote your 5 minutes contributed talk if you wish. And yep, so unless there are any other announcement, Jaco? No? Okay. No. So tomorrow, same place, same link. Again, I will send a reminder with the same link, and we will. I will also upload the videos later on today, so you can watch them again, and also send it to your colleagues if you want. All right. So thank you again,
thanks everyone.
Everybody.
See you tomorrow.
Have a great evening. Bye.